Hello, welcome to another lecture of CS360, and in this lecture we'll cover Rice's theorem. Rice's theorem is a theorem that essentially says that almost any question that you ask about the behavior of a Turing machine or of a program is going to be undecidable. So if you get a program as input and you want to ask something about what this program is going to do, then you won't be able to answer that question, except for a couple of caveats. First of all, we're only trying to claim that you won't be able to predict what the program will do, and not just other things about the program, like how many lines of code it has. Of course, you can answer how many lines of code a given program has. Just so the thing that you can't do is determine what the program will do. At least you can't determine this without running it. Okay, so if you run the program and wait for it to do its thing, then of course you will know what it did. But if you do that, then you won't be able to tell if this program is just secretly looping. If you're in an infinite loop, you won't be able to detect this fact. So it is not a foolproof way of determining what the program will do. So more formally, we want to say that for any class C, so here it's like I don't know, I'm not very good at writing this script C. Okay, let me just write a normal C. Okay, so for any class C of languages, so this is a set of languages. Okay, so for any class of languages C, we can define the language. So consider for a class of languages C, consider the set of all descriptions of Turing machines M, okay, such that L of M is in the class C. Okay, so this is a language. Okay, so C is not a language. C is a class of languages. It's a set of languages. Okay, but this thing here, this is a language. Okay, let's call this A. Okay, or maybe A sub C. It depends on C. Okay, so that is a language, and it's a language of descriptions of Turing machines, such that the Turing machine accepts. That the language of all strings the Turing machine accepts, that language is in the class. Okay, so for example, if C C might be, let's see, suppose C is a set containing the empty set. Okay, then AC is going to be the set of all machines M, such that L of M is in C, which is actually the only thing in C is the empty set. So this is equivalent to writing this, okay? Which is basically the set of all Turing machines such that M never accepts a string, never accepts any string. Okay, so it can either loop or reject, okay, but it cannot accept any string. So to decide AC in this particular case, we would be deciding whether an input Turing machine ever accepts a string, or if it rejects all the strings or loops on all the strings. Okay, so this is for any class C, we can define this set as this language. Okay, so for any class C, we have an associated language. And so Rice's theorem is almost saying that that this language is always undecidable for all classes C, but not quite, okay, because we can consider C to be the set of all languages A, such that A is recognizable. Okay, but then in that case, A sub C will be the set of descriptions of Turing machines such that the language of this is in C, which is the set of descriptions of Turing machines such that the language of the machine is recognizable. But note that the language of a Turing machine is always recognizable. So this is always true. So this is the same as the, the set of description of Turing machines. Okay, so if badly formatted inputs are not in AC, but any description of a Turing machine would be in AC. Okay, and this is decidable. So here AC is decidable. Just check formatting. So just check if the input string is formatted like a Turing machine, and if it is, then accept. Otherwise, reject. Okay, so AC is decidable in this case. Okay, and that's basically because because of this thing where every language of a Turing machine was in the class C. Okay, and a similar thing happens if every language of a Turing machine is not in the class C. Then a similar thing happens. So so we can't say that AC is always undecidable. We can say the next best thing to it. So we can say that, so call C non-trivial, if there exists M1 and M2. So these are Turing machines, M1 and M2, such that L of M1 is in C, but L of M2 is not in C. Okay, so here C doesn't contain all the languages of Turing machines because of the second condition, but also doesn't contain none because of the first condition. So it contains some but not others in terms of which languages of Turing machines it contains. Some languages of a Turing machine are in C, some languages of a Turing machine are not in C. So the question of whether, given a description of a program, given a Turing machine, whether its language is in C, this is a non-trivial question because sometimes it's yes, sometimes it's no. Right, so it's silly to ask this question if the answer is yes for every program, such as and it's also silly to ask this question if the answer is no for every program. So okay, so we call the language C non-trivial if for some programs its languages are in C, and for some others the answer would be no, the language is not in C. Okay, so then AC, okay, which again was this language description of Turing machines, such that L of M is in C. This is now a non-trivial language in that given an input M to know if it's an AC, you need to actually think about what L of M is. Okay, because for some L of M, the answer will be yes, and for other L of M, the answer will be no. Because you actually have to figure out what M is doing, what the language of M is. You have to figure that out at least a little bit. At least, it's not completely trivial, this question. Okay. So then that's the notion of non-trivial. So the Rice's theorem says if C is non-trivial, then AC is undecidable. Okay, so that basically means that, as long as you're asking a non-trivial question about the behavior of a Turing machine, about the language of a given Turing machine, I guess, if the question you're asking about the language of a Turing machine is non-trivial, then it's an undecidable question. And remember, this only applies if you're asking a question about the language of a Turing machine, not about. So it's only AC has the form description of a Turing machine such that the language of a Turing machine something is in the class C. Okay, but C can be anything. So it's talking about the language of the machine, not about other properties of the description of the machine, like the description length of the machine or how many states. So AC is only cares about the language of the machine. So for example, if I had this set, Rice's theorem does not apply. So this is cannot apply Rice, and we cannot apply Rice's theorem because yes, it's a language that consists of descriptions of Turing machines, but which Turing machines are in this language doesn't only depend on the language of the machine. It also depends on the number of states of the machine, or some other property of the actual machine, of the code, a property of the code, and not just a property of the language. Okay, so Rice's theorem doesn't apply here. Rice's theorem only applies when you basically build up a language of descriptions of Turing machines, and which Turing machines are in this language depends only on the language of that Turing machine, only on the behavior of that Turing machine, essentially, for which strings it accepts, and not on any other properties like how many states. Okay, so then you might be able to apply Rice's theorem if the class here, if the thing that's here is a non-trivial class. Okay, so that's the statement of Rice's theorem. So there's a few things to check if you're trying to apply to something to show that something is undecidable. You need to check, that you can really write your language in this form, where it only talks about L of M, and where the C that goes there really is not trivial. Okay, but after you check that, you get undecidability for free. Okay, so now let's prove Rice's theorem. Cool. So let's prove Rice's theorem. So so we're given C, right? So we need to show. So suppose by contradiction that P decides AC. Okay. So now so C is non-trivial. So we have machines M1 and M2 such that L of M1 is in C, and then L of M2 is not. Right, that was the definition of non-trivial. Okay, so now define Turing machine Q, and here's what Q does. So Q, it gets its own source code from the recursion theorem. Okay, and then basically, so it runs P on Q. Okay, so and then if P accepts, run M2 on W. Otherwise, run M1 on W. Okay. So this is the machine Q, and so now the question is, what happens? Like, is this description really in AC? And now note that if the answer is yes, if Q is in AC, then of course, this is equivalent to saying that L of Q is in C. Okay, so that's by definition of AC. So by the definition, so remember that AC, right, was the descriptions of machines such that L of M is in C. Okay, so so these are equivalent, Q being in AC, and so like if we look over here, Q being in AC is equivalent to L of Q being in C. Okay, so suppose that Q is in AC, then of course when you run P of AC, it will accept. And if P accepts, then what happens? So if P accepts, then Q just runs M2 on W, where M2 is this machine. Okay, so note that if P accepts this description of Q, then on every input W, Q ends up running M2 of W. So basically, Q becomes M2 essentially if P accepts here. I mean, there's this intermediate step where P is simulating, Q is simulating P on its own source code, but we've just said suppose that P accepts its own source code basically. So that first part always accepts. So essentially, what happens to Q when it runs on an input string W is it always run M2 of W. It just does the same thing as M2. Okay, so the language of Q then is the language of M2. So in this case, so basically, if this, then the language of Q is equal to the language of M2. But then the language of M2 is not in C. Okay, that was the condition here. Okay, so that can't be, right? But on the other hand, if Q is not in AC, then P will reject, right? And P will reject on every time, right? So the program Q essentially becomes a program M1. On every input W, P of Q will reject. And so on every input W, Q will just simulate M1 and W. And the language of Q will become the language of M1. But the language of M1 is in C. Okay, so if Q is not in AC, so let's write it here. If Q, the description of Q is not in AC, then the language of Q is equal to the language of M1, which is in C. Okay, so that's also a contradiction. So we get this kind of paradox thing. And we basically conclude that this P can't be right. It can't give us the right answer. And this contradicts the existence of P that decides AC. Okay, so it's not possible for a program P to decide AC. Okay, so it's a very short proof. It's again one of those paradoxy proofs, and it uses the recursion theorem to boot. But except for that, then it is kind of a short proof. And it's a kind of a very general and powerful theorem that tells you that almost anything you would ask about the behavior of a Turing machine is going to end up being undecidable. Up to these caveats that you got to make sure you're asking about the language of the machine and not about like how many states it has. And also, we're excluding trivial questions like, is the language of this machine the language of some machine? Like, yeah, okay, of course the answer is yes. So we're excluding trivial questions. But yeah, it's up to these caveats, then this is a very powerful theorem that can tell you that many things are undecidable in a very general way.